Hi everyone. So, for our project, we worked on implementing a PID controller for an RC car. Some background on the car. So this car was created by the Slick Science class, which is Engineering 2900. And even though it is an RC car, this car is actually not normally controlled with an RC controller. It's an autonomous self-driving car that travels to set waypoints using a GPS. So we found that the car drove great on flat, even terrain, but as soon as you get on a hill or grass or some uneven terrain, it either slows down or drives inconsistently. So in order to solve this problem, we came up with using a PID controller in order to fix that. What is a PID controller? Well, let me give an example in order to help try to explain that. So in our houses, we have a furnace AC system. And that system you set to a certain temperature, just like on our car, we'll set the car to a certain speed. And the furnace AC system will use that temperature, and it'll use the sensors it has to sense what the temperature is and try to adjust for that to get the correct temperature in the house. Just like our car will use its sensors in order to get the correct speed using its sensors.
So the whole point of this is to be able to tell this car we have here as a demonstration, if we wanted to go 5 miles per hour, we want to tell it go 5 miles per hour, and then it will be able to adjust whatever voltage is giving the motors to go fast enough for that. So a PID system, it's those three terms stand for proportional, integral, and derivative, if you guys remember calculus at all. But basically, we're not calculating a full integral, it's a numeric process. So it's pretty simple math. We take whatever speed we're going, and we have a GPS here, so that will tell us what speed we're going. We subtract that from our desired speed, and that gives us the error. So if we want to go 5 miles per hour, and instead we're actually only going 3 miles per hour, our error will be 2 miles per hour. And then we multiply that error by its proportional term, which is the P part of the PID. And then we find the integral of the error, so we find the error and multiply it by the distance the last time we ran the system. And then we find the derivative, so how much that error has changed. And we adjust these constants to figure out what it is. And add those all together, and that will give us the new output. So after we do all that, whatever that number is, that's what we give the motors and adjust, and it continually does this until it narrows in on our desired speed. Sorry.
And then just to kind of follow up on what Jake was saying, so what's kind of the role of the proportional, integral, and the derivative term? So the KP term, it's just some coefficient value that's being multiplied by the error. So if you have a positive error, then you're going to have a pretty big gain depending on what your KP term is. If you have a negative error, then that term is going to be negative. So the integral term is really there to basically allow for our steady state value to get as close to 0 as possible. So there's some systems where if all you had was a KP control, so you only had a proportional term and you had no integral or derivative, you'd actually never get your error down to 0. So we add in that integral term so that as time goes on, the integral term is going to remember what the entire error has been. So it's going to be able to drive your steady state down to 0. And then the derivative term is trying to look at, as we can see, it's looking at the rate of change of the error. So if you are closing in really fast on your speed, so if we want the car to go 8 miles per hour, and we see that it's going 4, and then 5, and then 6, and then 7, it's getting closer and closer to that set value, well, our error term is still positive, but it's going down, so we'd have a negative derivative there. And if it was speeding up to that desired speed really quickly, we're going to have a really fast, really steep negative derivative term. So that term is going to be adding into the positive first two terms and bringing our total throttle down a little bit. So the derivative term is so that you're not overshooting what your desired value is. That's kind of a little bit the roles. And this is just kind of a graphic that shows you what it really looks like. So you've got a set point here. So for our car, our set point is going to be the desired speed we want it to go. So maybe we want it to go 5 miles per hour. The actual output is kind of as read from a sensor. So for us, that's the GPS module. It's being used to tell us what the speed of the car is. We're going to compare those two, and we subtract the output from the set point, and that gives us our error. And then we take the proportional interval and derivative term, we sum all those together, and then that value is what we send to the actuator. The actuator in our case is the throttle of the car. So then we're saying, this is now what I want you to go.
So as we made our PID, so first thing is we had to write the code to be able to do all these things that we just talked about. And then the next thing we had to do was figure out what the constants are, because each of those terms we had a constant that we multiply it by, and that's how they call it tuning the PID controller, so that's how we can change how it behaves, which term dominates the output, and make them behave so that we can get our desired results. And then we had to make sure and test the car to see if it actually worked. So the first thing that we did is we just ran the car at different output speeds on flat ground. And we were able to get these data points and see about how fast the car goes given a certain output value. And that would give us our baseline for about where we want to be, so we know that we're not just way off. And this is a best fit curve just that we use to kind of plot and get our values for what we want it to be. And then this is our code. So right here, it runs it and it grabs the time that it happens, and then it calculates our delta t, so like how long it's been since the last time this code has been run, and then it calculates our error, so like it grabs what speed we're going and subtracts that from whatever desired speed is. That's our error, and then from there we calculate our integrals and derivatives, and we multiply it by our constants, and we add it all up, and then that gives us our output. And then it grabs the current time to use as the last time, the next time this code is run. Anything to add to that?
That was good. I guess the only thing I'd say is you might notice this part right here. We've got this else if statement if GPS.speed is updated. So one of the limitations of this system using the GPS to understand the speed is that it only updates at 1 hertz, so about once per second. So that's not really that fast. So what we didn't want to have happen was go and calculate what our new output was going to be, knowing that we're only actually getting more accurate information at a maximum of once per second. So we are only actually updating the information we're sending out to the throttle if the actual GPS has been updated. Otherwise, what we do is we have this final else statement that's returning this adjusted value, and that adjusted value takes on the value of our out, assuming this else if statement is run. And so the next time we come through the loop, if the GPS hasn't been updated, we tell it to go what we just previously told it to go. So it's not trying to update itself too much and get a wrong error because it hasn't updated frequently enough. So kind of one of the not as sciencey parts, if I can say that, of working with PIDs is coming up with the values for your coefficients is not really an exact science, but there are kind of guidelines that people use to understand. So one thing that we can do is initially set the Ki and the Kd terms, so the coefficients for the integral and the derivative portions to 0, and you start working with the proportional term. And so what you want to do is you want to get a value for your Kp term so that you have a desired value, your set point, and you notice that the output of the actuator is kind of oscillating around that value. So sometimes you're going above, sometimes you're going below, but you're just going above and below, and once you kind of get to that good place, okay, then you kind of can move into adjusting your Ki and your Kd term so that you narrow in on that actual desired value. And then finally, we have some graphs here that are showing basically what our results were. So this was using PID on asphalt and without PID on asphalt. You can see that it actually gets up to our desired speed pretty quickly after a couple seconds. It does oscillate around that value, but it gets up there a lot faster. Without PID, we actually take longer to get to our desired value, and we do overshoot it, though there might be some error here in the calculation of basically tracking the ESC speed versus the actual GPS speed. So that's what we see on asphalt. And then we went up a hill as well. This down here is without PID, so you can see that it goes up, it starts to slow down, and then it stops basically once it gets to a certain point. So without using PID, we basically just go a tiny bit up the hill, we get stuck, and then we stop. We can't go further. With the PID, it's better. It's certainly not perfect. But what happened was we would go up, we'd stop, we'd go up again, we'd stop, we'd go up again, we'd stop. So at least we're getting further up that hill having PID input as opposed to really not moving up it at all. We also tracked versus time the ESC value, so the int value we were sending to the electronic speed controller. And we noticed it started oscillating between 110 and 90, which on a previous slide was the constraint we had on the function. So we never wanted the output to get above 110 or below 90. So this is definitely something that tells us our coefficient terms need to be adjusted, other stuff needs to be adjusted so that we're not hitting these constraint values, or maybe we have to adjust that constraint output.
So our current implementation, it seems to work, but it's definitely not perfect. There's definitely things that we can continue to work on to try to improve it, and one thing she mentioned was just tuning these constants, so we can just tweak the constants till we hopefully get a desired value. But also with our car, we might just have limitations because the car's GPS only updates about once a second. And so we're not getting that information fast enough maybe to be able to actually do this. So we might need to get a new GPS module, which there are ones that update about 15 hertz, so 15 times a second. That would give us a lot of information, a lot more information to hopefully make finer adjustments to achieve that speed. And then the last thing that we would think would probably be the best option is to build an encoder and put that on the wheel, and that would just be able to tell us the speed at any given time, and so that we can make much finer adjustments and be able to make a much smoother, maybe go that speed and just stay there instead of our oscillations that we were seeing before. But so far it works, but there's definitely things we can improve. I think that's our presentation. Thank you.
We have about 2 or 3 minutes for questions.
Yeah.
You talked about making improvements. Have you already experimented with those improvements and did they show any results?
So we have not experimented with them yet. Those are ideas. So we just barely have done this. We didn't have time to do all those other things, but those are our ideas of things that we could do to make this work even better.
The one adjustment we could do right now is adjusting those coefficient terms, because we could test all day just like barely changing those values and kind of see the results, and that's kind of what we tried to do. When it comes to the GPS module, we just have to buy a different GPS module that would update faster, and then the encoder is something we'd have to put on the wheel so it tracks the rotation. So those are definitely possible adjustments, but just need more time or more money or something that's what we don't currently have the hardware for. So.
Do you use the GPS for anything other than measuring your distance to get your velocity, or are you using other?
So we do. So when we were doing this testing, we weren't. So that's actually something interesting. But these cars are used for a summer camp for middle school students, and they're able to run through a course. You have like set waypoints on GPS coordinates, and it's able to go that one, then that one, and that one. So we do usually use it. But when we were just testing the PID, we weren't.
That's the main purpose of the GPS, is to like get from this coordinate to this coordinate autonomously. And we just realized that, oh, the GPS also will give us speed. So that's one way we could implement PID control.
Part of the reason we weren't using the GPS in order, to drive from one spot to another is these cars won't necessarily drive perfectly straight. They'll kind of correct themselves. And we're trying to get a consistent speed in order to test our controller. So that's part of why we didn't use that.
All right, thank you all